All right, so again, thank you for your patience, everybody. As we get to the end of the year here, it seems like the tests are taking a little bit longer for every person to finish up. So 7.5, we talked about exponential equations on Thursday so that you wouldn't have to watch the video on Friday and you could just go ahead and do the homework. But that means we left those logarithmic equations for today. So we're going to start off with an exponential just to remind us what we were doing last week, and then we'll go into the logarithmic. This says, for resource management, wood is a sustainable, renewable, natural resource when you manage forests properly. Your lumber company has 1,200,000 trees. You plan to harvest 7% of the trees each year. How many years will it take to harvest half of the trees? Now, this one, especially, I wanted to wait until after we got back to talk about this one, because this does use formulas from 7.1 and 7.2. And that was one of the reasons that I had you do that review worksheet before we started this. If you're taking trees out of the forest, is the number of trees going up or down? I know, it seems like a pretty obvious thing, right? Well, the only formula we had where things went down was called the depreciation formula. But it works for anything that's going down, so that's what we'll have to use. And A, again, is the initial amount, which unfortunately for us is 1,200,000 trees. Make sure I get all my zeros in there. All right, we got it. And you're going to harvest 7%. So we don't put in 7, we put in 1 minus 0.07. And we want to know how many years it's going to take to harvest half of the trees. So the first thing I think of is, well, they didn't give me what half the trees is. They don't need to give us what half the trees is. If we have 1,200,000, we can find half of that, and that would be 600,000 trees. Like so. Now, things to simplify. Pretty obviously, we should be able to do $1 minus 7 cents in our head, right? So 93 cents. And now, instead of what we did in 7.1 and 7.2 was, hey, let's make one side y sub 1 and the other one y sub 2. We're going to solve this with logarithms now. So we'd look at it and say, I need this to be by itself. The base has to be exposed. So I'm going to have to divide both sides by 1,200,000. Well, and I already know what 600,000 over 1,200,000 is because I had to find that before, half of it. So this should be a half. Now, using our thinking from Thursday and the assignment you did on Friday, what should we do to both sides of this to solve it? Logarithm base 0.93. Because when those match, they're inverses of each other and they cancel out. Now, since it already has decimals in it, I'm going to go ahead and change this side in a second, but right now I need everybody to see that that's just going to be t, whatever that is. Never cool in a math problem to use both decimals and fractions. So, logarithm of the big one, and I mean size-wise, that we're trying to evaluate, that'll be 1/2. But I'm going to change that to 0.5 since we have the other one as a decimal. And then logarithm of the base goes on the bottom. And then we just punch it in, and we figure out how long is this going to take. So log of 0.5. Oops. Log 0.5, there we go. Parentheses, don't forget to finish those up, divided by log 0.93, parentheses. So about 9.5 years. 9.55, we'll go with 9.5 years. Because usually when you get to college algebra and pre-calculus, we ask you to interpret that. And that means you just have to write a sentence telling what's going to happen. So they will have harvested half the trees. In approximately 9.5 years. So you just kind of write a little summary. That's called interpreting your results. So they decide that's too fast or that's too slow, and that the reason they're doing this is because, like they're saying, this is really a logging company wants to do this. Otherwise, they run out of trees, and then they have to lay people off and all that good stuff. So 7% of the trees each year, they're going to find out that about 10 years, half of the trees will be harvested, and they can plan ahead. Where do we plant the trees? Where do we get new ones? But for some reason, they decided that wasn't working, and they changed it. They said, we're taking too many trees at one time. After how many years will you have harvested half of the trees if you harvest 5% instead of 7% yearly? And that tells us the only thing that's going to change was our little 0.07 becomes a 0.05. Everything else is the same. So instead of 93 cents, what do we have this time? 95 cents. Still going to get 1/2 or 0.5 over here. So can we use logarithm base 0.93? That would be silly. What base should we use? Match what we have. These will cancel, and then we can use the change of base formula on the left-hand side. So logarithm of the larger number that we're trying to evaluate over the logarithm of the base. Because when I say large and small, I mean size. I don't mean value. This one is written bigger, the number that we're trying to evaluate. So log 0.5 over log 0.95. 13.5 years, 13.51, and if we wrote our little sentence again, we'd say about 13.5 years. Now, how do they know which one of those to do? Well, it depends on how fast their trees are growing. If they realize, oh, you know what, 10 years, they're really not totally mature yet. Let's give them a couple more years so we can get some good 2x4s, even 2x6s out of those pine trees. And here they've said, yeah, this is what we have to do. Let's go a little bit longer with this. And then we'll have it sustainable. We'll keep we're making trees by planting trees, and we'll keep using those trees to harvest. So now, after that brief little introduction from Thursday and Friday's material, we're going to switch gears. And we're going to talk about solving logarithmic equations. So here's what was going on. We had a base that maybe we had to get it by itself. And then we could take the logarithm. And it worked out great because what you do to one side, you do to the other, followed all the algebra rules. These are logarithmic. So they have logarithm in the problem to start with. And these we have to do a little bit differently. But I hope you've noticed that this chapter isn't necessarily the toughest stuff we've ever done, right? So this can't be something that's horrible to solve. So let's see here. Solving a logarithmic equation. What is the solution of log 4x minus 3 equals 2? And I'm going to tell you, because this one only has one logarithm on the one side, and that's the first step, by the way. You have to isolate the logarithm, get it to be just one by itself. Sometimes that means you have to condense something. But we already know how to do this, because when you solve a logarithm, you snail shell. So what's the base? 10. Let's snail shell. 10 squared equals 4x minus 3. we said early on, you can't really understand logarithms until after you've done a bunch of these. So it's easier to get rid of logarithms and think of them as exponential equations. And that's what's going on here. Now 10 squared we know, because that's 10 times 10. That's 100. And this is just algebra. Now again, the fancy name, not snail shelling, you're not going to see that in your book, is exponentiating. And that's what we're doing here to solve it. So we're going to add 3 to both sides and divide by 4. Again, most of the time they give these as decimals. So let's just punch it in real quick and write it both ways. 25.75. So isolate the logarithm. Get one logarithm on a side, on one of the sides of the equal sign, and then snail shell. Exponentiate. That's what we have to do. So, talk me through this one. It's log of 3 minus 2x equals negative 1. What should we do? LOG without a base is always 10. So snail shell it, 10 to the negative 1 equals 3 minus 2x. Now, 10 to the negative 1, you could leave it in there if you're going to do decimals all the way through, but that would drive me bonkers. Because one of the things we have to do on the non-calculator portion of this test is remember that negatives are for fractions. So we'll put a 1 on the top, and 10 to the first is 10. Then we'll do the math. Let's subtract 3 from both sides. So now I'm going to do the whole common denominator thing, but again, you could do this in your calculator and get your answer. But we've got 1/10 minus 30/10, because that's what 3 would be, and that's going to give us negative 29/10. And because I have a fraction over there, I'd probably multiply by the reciprocal instead of dividing by negative 2. So multiply both sides by negative 1/2. Top times top, bottom times bottom, 29/20. Again, if all the answers are decimals in the back, they do that a lot with logarithms. We just punch it in. 1.45. And there it is. So as long as there's just one logarithm on a side, this is pretty sweet. All we have to do is snail shell, and we already know how to do that. And then the algebra steps after that, we definitely know how to do. And then we get to problem 6. And you had to know it was coming. They say, all right, deal with this. Well, let's see. In order to solve this, I have to have one logarithm on one side. Wait a second, we know how to do that. That's condensing. What does addition mean in logarithm language? So let's just write it as log x times x minus 3. I'm going to put in an extra set of brackets here so nobody loses track of it. You wouldn't need them if you can keep track of everything going on there, but when somebody looks at the notes, I want them to see we multiplied those two pieces together. Speaking of multiplying, let's go ahead and do that. Let's distribute those two. Now we have isolated the logarithm on one side. So what do you suppose we should do? Yeah, what's the base? It is a 10. 10 to the first equals x squared minus 3x. Ooh, this just got interesting. As I start to solve this, is the x squared going to disappear? We have an x squared on both sides, so when we try to subtract, it'll be gone. So that means we have to solve a quadratic. Anybody remember how we solve quadratics? Set it equal to 0 on one side. So I'm going to go ahead and subtract 10 from both sides. Then what should we do? Yeah, if we can factor it, we're going to factor. Now, there is no greatest common monomial factor. It is not a perfect square trinomial because there's a negative 10 in the back. But I'm pretty sure we know two numbers that multiply to negative 10 and add to negative 3. What are they? So what are the two solutions? 5 and negative 2. Unless one of them doesn't work. So we have to check these. The one I'm really worried about is the negative one. Remember we said our bases are always going to be positive. So negative, let's check it out and see what happens. So if we go back up here and put in a negative 2, it's going to say the logarithm of negative 5 plus the logarithm of negative 2. So we got a problem. Well, if that one doesn't work, maybe 5 works. And again, you could quick put it up there and just make sure it's not going to make anything negative. And you could also punch this one in. I don't know if you realize that, but this one's a logarithm base 10. So this would be logarithm of 5 minus 3, logarithm of 2, plus logarithm of 5. Well, let's check. Logarithm of 2 plus logarithm of 5. Yep, it's 1. So that one's good. So be very suspicious of negative answers. Sometimes they work, but a lot of times they don't. Alrighty, what's the solution to that mess? Oh goodness, that's not one logarithm, is it? How do we get it to be one logarithm? Yeah, division. Subtraction in logarithm language is division. Hey, we can simplify that. 3 goes into both 6 and 3. Now what should we do? Snail shell, what's the base? Yeah, I wish they would have been a little creative with this. Everyone we've had so far is at a base of 10. They don't have to be 10. 10 to the negative 2 equals 2 over x. 10 to the negative 2. Not a negative, just 1/100th. Because the negative is for bringing it down to the bottom. It'll be like this, 1 over 10 squared. Oh, I think we knew a really easy way to solve something that looks like that. What do? Yeah, it's a proportion, cross multiply. Now we're feeling good about that answer, but since it was base 10 and we can plug it into the calculator, why not give it a check? So log of 6 minus log of 600. Well, look at that. It's negative 2. And that's what the other side said it was supposed to be. So this one is good. So today we went over an example that still had the exponential where we had to take the logarithm of both sides. So that was the first part of the objective, solving those exponentials. And now we've solved logarithmic equations too, and I think we're out of stuff. That's the last one, isn't it, in your packet? Yeah, so so far so good, right? Chapter 7, looking pretty good. Let's get you some work time here on 7-5 day 2. It's like some people have to wake up a little bit before they get going today. Again, you want, calculator handy, whether or not it's on the Chromebook or it's, sitting on your